In lesson 1.5, we're going to talk about polynomial functions and complex zeros. A lot of this hopefully is a refresher of some basic concepts from Algebra 2. So one of the first things that we talk about here is imaginary number. And they define imaginary number right here, where we see it is a square root of a negative number, and that square root of -1 is equal to I. So if we simplify the square root of -9, you can see how that breaks down, and it ends up being 3i. Now, the other kind of piece to this that you hopefully have seen before is that we have imaginary and complex numbers. A complex number is in the form of a plus bi, where a is the real part, so a tangible number, and bi is a coefficient times the imaginary number, just like what we saw with the 3i. This would be the bi part of it. This is a pretty important theorem, aka fundamental theorem of algebra, and it basically says that that any polynomial function with a real number coefficient can be factored completely over the set of complex numbers. Every complex polynomial function f of x of degree n is greater than or equal to 1 can be factored n, this is important, linear factors. So what does that mean? Well, it means that if you have something like x cubed down here, we should be able to break that down into 3 binomials. So it's factored into 3 different parts. If the degree was 4, it should be factored into 4 different parts. Now, some of it's going to be easy where it would be factorable and you can clearly see what those are. Some of them take a little bit of work. So if we take number 1 for an example, we can see that we can take out an x from this polynomial. But when you do that, you'll notice that that trinomial is not factorable. There is not a number that multiplies a 13 that adds to -6. So think about what that means. You usually factor to solve for a solution, and the solutions are your zeros. So what would be another way to solve for the zeros or the solutions of this right here? Well, that would be the quadratic formula. So I can use the quadratic formula to help me find out what the zeros are. So opposite of b, plus or minus b squared minus 4ac over 2a. And I'm going to reduce that down, and we're going to get 6 plus or minus the square root of -16 over 2. And remember that -16 is going to become 4i. And then I'm going to reduce that down just a little bit more and get x equals 3 plus or minus 2i. Now again, these are your solutions, okay? These are your solutions to that polynomial. And so what this is saying is that we should actually be able to factor it. So the zeros, let's go back. The zeros are, or the solutions are 0, and that comes from this one, if you set that to 0. The other solution is 3 plus 2i. The other solution is 3 minus 2i. And what you do with these to do the fundamental theorem of algebra is we're going to put it in its factored form. And the factored form basically just takes this and puts it into a binomial. So you're going to get x minus, this is where you have to be a little bit careful, the quantity, I'm just trying to get a different ink color, 3 plus 2i. And then x minus the quantity. Three minus 2i. And then that 0 right here, that was already, or that x equals 0 was already factored out. Now, what I'm going to do now is distribute that negative. So it's x minus 3 minus 2i times the quantity x minus 3 plus 2i. So this would be the completely factored form. So even though that, this right here are complex numbers or in imaginary numbers, they still can be factored, help factor down a polynomial. We're going to use that idea to help factor completely this expression. So you can see in this case, we have a y in both terms. And what's going to happen, it's a 25, I need to factor this down. And again, this isn't up dots because it's not a minus, so I can't just do 2x minus 5, 2x plus 5. So I kind of take that idea and I do 4x squared plus 25, and I set it equal to 0, because if I solve for it and solve for the zeros, that tells me the solutions that help me find how to factor it. So I'm going to go ahead and solve this. And what you're going to notice is that I'm going to have negative 25 over 4. So when I take the square root of it, remember when you take the square root of it, it is plus or minus, but there's that negative. So square root of 25 over 4 is 5/2, but it's that I. And then there's 2 of them. So this factors in to x plus 5 over 2i times the quantity x minus 5 over 2i. And then we're going to drop down that y. We started talking about end behavior in the last section, knowing how the degree alters what direction the end behavior is in the leading coefficient. And that kind of helps us sketch the graph. The same can be said when you talk about the zeros of a function. And knowing whether it's an even or an odd multiplicity can really help us out. So if a polynomial function has a factor that is repeated, these duplicate roots are labeled as a multiplicity of n. And I'll show you what that looks like in just a minute. If the function f has a real zero c of odd multiplicity, then the graph of f will cross the x-axis at c comma 0. Again, we'll talk about what that means. And then if the function f has a real zero of c of even multiplicity, then the graph of function f will be tangent to, which means basically just touches, like gets right to the graph and bounces off at the x-axis at c0. So this is going to be very helpful in sketching graphs. And so knowing this will kind of decipher the behavior of it and help you draw quicker graphs than actually having to like make a t-chart or anything like that. So if we look at this, in example number 3, they have this function sketched out. Now, first of all, let's talk about this. If this has a degree of 3 and this is a degree of 2, right, and this is factored and you multiply it out, this has a degree of 5. This coefficient is positive 1, this coefficient is positive 2, so that leading coefficient is 1. And think about that end behavior. It should be split apart because it's odd, and it's going to rise, so the left goes down and the right goes up. And it kind of has that upward mobility slope, which is what we see in the graph. Now, what other things are helpful? This is what this multiplicity is. So right here, the multiplicity of x plus 2 to the third power. That means that you have x plus 3 times. That's the multiplicity. It doesn't mean just that there's one kind of solution there. It represents kind of 3 zeros within one. And then same thing with this x minus 1. This is also a multiplicity, but of 2 in this case. Now let's go back to this one, this x plus 2 to the third. Because it is odd, it means it just passes through the graph. And you can see that, right? It goes up, it doesn't bounce back down, it just goes through the graph. All odd exponents will do that, and odd exponents will just carry through the graph. Whereas if you have an even exponent, it will bounce off of it, and that's tangent, right? So the graph is tangent to it. Now think about this in other respects. Let's say we had a linear line, and that linear line, right, y equals mx plus b, that degree is 1, and think about a linear line. It goes straight through the line, okay? Because that exponent is 1, it's odd. Now, we'll kind of see this a little bit later, but do you see how that concavity kind of changes? It kind of lingers right there. That's going to tell you it's going to be a higher level exponent versus the 1. And same with this. If it just quickly bounces, it's going to be a lower one versus if it's more flat and then comes up, then it's probably going to be a higher because of that difference in concavity. But for right now, what we want to know is an odd 0 goes through it, an even 0 bounces off of it. So it wants us to label the zeros and describe the behavior of the root. So what it just wants us to say is that at x plus 2 cubed, it's odd, and that is at negative 2 comma 0. And then we have x minus 1 squared, that is even at 1 comma 0, so those x-intercepts. This has x equals negative 2 has a multiplicity of 3, and x equals positive 1 has a multiplicity of 2. This right here, we already talked about this. This is tangent to the x-axis, and this crosses the x-axis. So number 4 is asking us to look at the graph, and based on the graph, it asks us what's the smallest possible degree of h of x, knowing our knowledge of zeros. Well, if we look here, here's a 0, here's a 0, and here's a 0. This one just passes through, and this one passes through, so that means it has to be an odd degree. This would also imply that there's 1 degree here. So that's like 1. This passes through, so this would imply a degree of 1. This right here, because it's tangent to the graph, it bounces off. It would imply that it's an even exponent with a minimum of 2. So if we add those up, that would be 4. And that's really our justification. So a minimum degree of 4. And because the zeros at x equals negative 5 and x equal 2 pass the x-axis, it implies a degree of 1. Excuse the terrible handwriting on the tablet. And then also the zeros, 0, well, no, it's zeros, there's 2, at x equals negative 2 is tangent, meaning it bounces off. It implies even, which is 2. So 1 plus 1 plus 2 gives us 4.